Hello, Calc BC. We're here to learn about U substitution today. This is an extremely powerful technique for solving integrals, and it's honestly the first thing that I usually use when I'm trying to solve a difficult integral. You can kind of think of this as like it's the Kanye West of integrals. It's the biggest tool we have. So here's the question that it helps us with. So we can do an integral like the square root of x, or we can integrate something like the sine of x, hopefully. But what about if there is more in parentheses? So what if you have to integrate the square root of 2x minus 4? Or what if you have to integrate the sine of 3x plus 1? Okay, and what we're going to do, the general strategy of U substitution, is we're going to substitute in a new variable u. So instead of writing our integral in terms of x, we're going to write it in terms of u, and that's why it's called U substitution. And you can think of this basically as the opposite of the chain rule. It's somewhat like the chain rule for integrals, not quite as powerful, but it's going to be pretty good for that. Okay, so let's go ahead and do several examples, because this is a strategy that I can really just show you by doing a bunch of examples. So suppose we integrate 2x times e to the x squared. Now the first thing you're going to want to do, if you want to transform it into a new variable, you're going to want to pick which variable is u. And what you're going to pick for your u, it is usually going to be in parentheses or implied parentheses, and it's often something that is raised to a power, or in this case, inside a function. So in this case, instead of just taking e to the power of x, I have e to the power of x squared. So that's what I'm going to choose to be my u. Okay, so u is going to be x squared. Now, the next thing I need to do is I need to go ahead. I'm not just going to write this in terms of u there. I need to make, like instead of dx, I need to make that to be in terms of u as well. So I'm going to take the derivative of u to find du. Okay, so when I take the derivative here, my du dx is just 2x, so that's saying du equals 2x times dx. Just kind of multiply the other side of the fraction by a dx there. Okay, so that's how you find the du. All right, so once you have your u, and once you have your du, which is the derivative of u, basically what we're going to do now is we're going to plug in the u first. So instead of being e to the x squared, I'm going to write that part as e to the u. And then for the du, what I'm going to do is I'm going to put in the du by replacing the dx and possibly some other parts with a du. So when I look at this, I have a 2x times e to the x. So I'm going to replace the 2x times dx. So I could rewrite this, right? I could write this as like e to the x squared times a 2x dx, and then replace that whole thing with the du. So I'm just going to rewrite that as e to the u. Okay. And what I've done here is I've taken a slightly complicated integral in terms of x, and I've written it in terms of an easier integral of u. That's the point of U substitution. Write it with a new variable, and now we have a simpler integral. Now, all we need to do is integrate. And then we're going to plug back in. Okay, so the integral of e to the u du, of course, is just e to the u plus c. But what I want to do now is just plug this back in for the u here. So that'll just be, so instead of writing e to the u, I'll write e to the x squared plus c. Okay, now this makes sense, because if I take the derivative of that in my head, I have e to the x squared times 2x, which is what I started with, so we're good to go. So that's how U sub works, and let's do a couple more examples so we can see kind of what's going on. This one's going to add one more kind of kink to our plan. So what if we try and integrate the sine of 3x plus 1, something I alluded to earlier. Okay. Now for your u, what you want to do is you want to choose the part in parentheses. So pick the u to be 3x plus 1. Now when I take the derivative of that, the derivative there is 3, so my du is just 3 times dx. So just take the derivative, put a dx on the end. Okay, now what you might notice is there's no 3 in here. Like we are missing a constant. So if we're missing a constant, what we're going to do is we're just going to randomly put in the constant to match. So we're going to put in the constant to match the du. So I need a 3 dx, so I'm going to put a 3 in here. Now, I can't just randomly put a 3 in. I can't just randomly multiply my integral by 3. So what I'm going to do is multiply by 3, but also multiply by the reciprocal. So what I'm also going to do is I'm going to balance it. I'm going to balance that 3 with the reciprocal, and I'm usually going to put that at the front of the equation. So I'm multiplying by 3, I'm also going to multiply by 1/3. Okay, so I'm not changing my equation. I'm multiplying by 3 and 1/3, so it doesn't actually change it. But that allows us to rewrite this as 1/3 times sine of u, because this is just sine of 3x plus 1, and then that whole 3x turns into a du. It gets replaced with a du. Okay, and now this is an integral you can do, right? So we know how to integrate sine of u, so that's negative 1/3 times cosine of u plus c. So when I plug back in, it's negative 1/3 times cosine of 3x plus 1 plus c. And again, when I take the derivative in my head, I get back to what I started with. I get back to that sine 3x plus 1. So that's the trick on this problem, right? Filling in that constant to match. We needed a 3 dx, so I had to put in the 3 here, and then I had to balance with a 1/3 in front. That's how you want to approach those problems with the constant. Let's do a few more examples here. So let's suppose we have to integrate x times the cube root of x squared plus 1 dx. Okay, so let's see. Hopefully your choice for the u, your first choice should be the x squared plus 1, because that's kind of what's in parentheses, right? That's just being raised to a power. My du is 2x dx. Now, I already have an x dx, so I need to put a 2 in here, and then I need to balance it with a 1/2 in front. And a lot of times I'll just put that in front of the integral, because it doesn't matter, right? You can pull a constant in and out. Okay, so what that's going to become, 1/2 integral. The 2x and the dx, that becomes a du. And then the cube root, that's just u to the 1/3 power. Okay, and now we're chilling. Now we're not too bad. So we add 1 to the power, so u to the 4/3. We have a 3/4. You know, generally once you do the u sub, it should work out to be something that's pretty easy. We want to write it back in terms of x. That's 3/8 u to the 4/3 plus c, and then we're going to plug in for the u. So that's just going to be 3/8 times x squared plus 1 to the 4/3 plus c. Okay, so that's kind of the basics of this. Let's do a couple more just so you can kind of see what this is going to look like. Let's take a look at another example. This one's a little weird. You do 1/4x plus 2. Now, you might look at this and not immediately think of it as a u sub. And I would say you're probably right, except there is something raised to a power here, right? So one thing you could do is you could just pick the u to be the denominator if there's no exponent. Because if you pick a u to be 4x plus 2, and then your du is 4 times dx, well, you're going to rewrite that. That's just 1/u, right? And we know how to integrate that. Okay, so when I need to match the 4 dx, I put a 4 here. I'll balance with a 1/4 in front. So it's 1/4 times 1/u times du. So then that just becomes 1/4 times the natural log of absolute u. And then I'll just rewrite with an x, 1/4 ln of 4x plus 2 plus c. Okay, so well, that's another idea. If you don't see an immediate fraction or an immediate exponent, just pick the denominator of your fraction to be your u and see if that'll work. If you pick a u and the integral doesn't look really easy after you substitute it in at this step, then you screwed up. Then maybe that's a step you need to go back and pick another u. Let's take a look at a similar example. Let's say I ask you to integrate cotangent of x. Now, you might look at this and say, bruh, how am I supposed to integrate this? This has nothing to do with the u sub. I don't see any parentheses, any exponents, nothing. But trust in the math. So let's see if there's a way to rewrite cotangent. Because can't I write this as the integral of cosine of x over sine of x? Because that's what cotangent is? Ooh. Now I see I could do something like the last problem. I can choose my u to be the denominator. And then when I take the derivative of that, I have cosine x dx, and how convenient I have a cosine of x dx. Outstanding. So this just becomes the integral of du over u, so just ln of u, so that just becomes the natural log of the sine of x plus C. How beautiful, right? If someone asked you to integrate cotangent, you probably would not expect it to be something with a natural log. That's kind of cool. So let me show you one more. Here's another situation where you have a u sub. Say you want to integrate 1 over e to the 3x. Now, if you put an ln in this, I will slap you whenever I'm physically able to do so. What you want to do when you see an integral like this, rewrite this as e to a power. So I can rewrite this as e to the negative 3x dx. And then when I want to integrate that, my u is going to be negative 3x, so the du is negative 3 dx. Okay, and now we're okay. Let's put this in a different color. So we need a negative 3 in here. We put a reciprocal negative 1/3 in front. So that becomes negative 1/3 integral e to the u du. Okay, and again, when you have that, e to the u is e to the u, so that's just negative 1/3 e to the u plus c. Didn't mean to make this so Eurocentric. So this is negative 1/3 e to the negative 3x plus c. Okay. And again, when you take the derivative of that, the negative 3 multiplies and cancels, you get e to the negative 3x, and you're good. Okay, one quick warning that I wanted to give you guys. Actually, two things. One is that if you have, say, for example, integral x plus e to the 2x, like something like this, you obviously have to do a u sub on the second part. What you should do is you should split this into two integrals. Don't try and do a weird u sub with the first x. Just split this up and say, okay, I'm going to integrate x, and then I'm going to integrate e to the 2x, and then just do a u sub here. Okay, and the last thing I wanted to share with you, this is more of a quick note. If you have to do the integral of cosine of x squared, a u sub doesn't work here, and I'm going to show you why. Now, hopefully you would look at this and say, well, bro, my first indication would be to do a u sub to be that part in parentheses. So if I do u equals x squared, then the du would be a 2x dx. Now, I could put a 2 in, but I don't think I can put an x in. Because I put like an x here and a 1 over x in front, but then I can't like move that outside. I'm not able to move an x outside, only a constant. So here's a good general rule. This doesn't work. You cannot do a u sub if you have to add in an x. Like you can add in constants all day, but if you have to add in anything with an x, a u sub is not an appropriate strategy for that problem. Okay, so that's U substitution indefinite integrals. Thanks for watching. Bring some questions, and I'll see you guys soon.